Welcome to Multiple Choice Question 21 of the 2009 Mathematical Methods Exam 2. In this video we will be looking at the solution for this question. A reminder that this video is in no way endorsed by VCAA. And now before we move on, I'd just like to point out that the use of the CAS calculator is not really appropriate for this question, as there's no way to input the information given into the calculator. So for question 21 we're told a cubic function has the rule y equals f of x. The graph of the derivative function f dashed of x crosses the x-axis at 2, 0 and at negative 3, 0. And we know that the maximum value of the derivative function is 10. And we are asked that the value of x for which the graph y equals f of x has a local maximum is one of the following. So if we have a cubic function to start with, the derivative function must be a quadratic. And as we know where it crosses the x-axis along with the maximum value of the derivative function, we could actually start by graphing it. So we know that it has a maximum at 10, which means that it must be concave down, or this direction for the parabola. We also knew that it had a x-intercept at minus 3, 0, and a second one here at 2, 0. And just labeling that point, that was a maximum value of 10, and we know that the maximum value of a parabola occurs halfway between the x-intercepts, so technically we know that that's at negative a half. So the question that we're really being posed is the value of x for which the graph of y equals f of x, the original graph, has a local maximum is one of the following. So it would be tempting to select E as our answer, but we have a local maximum on our derivative graph there, not on our original graph. So we need to think a little bit more deeply about what exactly is a local maximum. So we know a local maximum looks something like this, and that means it's characterized by having a positive slope or positive derivative value slightly to the left of the value, a gradient of 0 at the point, and then a negative slope or negative derivative value for x values greater than where the maximum has occurred. We need dy dx, the derivative graph, to be positive, so we need to start in the positive region. Then we need it to go through 0, which happens when x is 2, and then we need the gradient to be negative for x values bigger than that. So that means this point here is a local maximum, as we have positive derivative values, 0, and then negative derivative values. So that characterizes a local maximum, so our answer to this question is 2. And just so you know, this point here would be a local minimum, because it would have negative, 0, and then positive gradients of the tangents along those points. So that bit there on the derivative graph characterizes a local minimum. From the examiner's report, we can see that this question was quite poorly done, with only 43% of students getting this question correct. And as you could see, it was a bit of a jigsaw puzzle to put together on the previous slide, and you did need to think pretty deeply about what it meant to be a local maximum and how we could extract that information out of the known information that was given for the derivative function f dashed of x.